clean.bat, your project will probably be about 35 megabytes. And it won't go up, won't go up, won't go up. Tears running down your face, it won't go up, I'm going to lose points. If you clean with Visual Studio, it may be under 25, but may not. But if you then run clean.bat, so you need to put it in your, either put it someplace on your path or put it down in your project folder and then navigate, pull up command prompt in your project folder and just type in clean, and you'll see it deleting a whole bunch of stuff. PCH files, SDF files, IL files, and so on, IPCH files, and a whole bunch of really big stuff that you don't need, and the Visual Studio will reproduce. So do that before you attempt to upload, and don't wait until 11:45 because you won't make it. Every time there's a project, I'll get 4 or 5 emails. Please, 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 please. I was only a minute late. I couldn't, it wouldn't take my upload. It wouldn't take my upload. It took me until a minute after. And you'll get back a reply from me, -1. Okay. No mercy. You were warned. Okay, so even if it's a nanosecond after, if it has a time date stamp of Wednesday's date, which it will have a nanosecond after midnight. Well, maybe not a nanosecond, but okay. Then a microsecond after midnight, then you'll lose a point. Okay. Are there any questions about Project 1 before we start, resume with the template material? Good. Okay. There is now a Project 2 Help Spring 18, and there's a tree walk demo in there that shows you how to walk through a linked tree recursively and using stacks and queues. And you're going to need to be able to walk through directory structures with in order to find files and stuff. You may need to, depends on how you design project. A robust design would. But also, you're going to need to walk through the dependency relationships in your database. And those are not a tree, those are a graph. They may be a graph. And so to walk a graph, there's one little added piece. If you walk a tree, there's no cycles, and there's no cycles in a tree. Okay, can't be by definition. So you just walk, you visit every single node, and you're done. But in a graph, if you have mutual dependencies and you don't do something about it, you'll just sit there and spin and spin and spin around on that mutual dependency. And what that means is if you're doing a recursive walk, you'll blow the stack. Bang, gone. And if you're doing it with a, so what you have to do is mark the places you visited. And so if you're coming around and you're beginning to look at something and it's already marked, you back up, you backtrack, okay? And I will do a demo. I haven't done that for you yet. I'll do a demo that says graph walk demo that illustrates that. And I'm not going to walk your database for you. I'm not going to write that code to walk the dependency relationships in your database code. You need to make queries and get that relationship, and walk it. But I'll show you how to do the traversal. Doesn't mean that you have to build a graph. It doesn't mean that you have to query your database and then build a graph in memory. It turns out that database is a virtual graph, and you can walk that if you set it up appropriately. No, if you do build a graph, that's okay. But anyway, that's there. I'm not going to put as much stuff in Project 2 Help. By now you're getting to be hardened, hardened developer. You don't need as much help. I will give you quite a bit of help for Project 3 because we're going to be working with socket-based communication and threads, and you need a bit of help with that. But again, on Project 4, I won't give you much help. So Project 1, a lot of help. Project 2, not much help. Project 3, a lot of help. Project 4, not much help. Okay. All righty. So templates. Now, we should be at lecture 7, and on the college server, these links are broken. Somebody just pointed that out to me. I don't know whether the, I think the problem is that I didn't upload. I've been shuffling code around. Remember I told you that I have this configuration management problem, and I've been moving code around, and I think I didn't get it. I moved it on my machine at home, intending to copy it up, and I forgot to copy it up. So I will take care of that right after this class. So those links should be active by this afternoon, but right now they aren't. I'm on my machine that has all the code in place, so we'll use that. Let's finish up the templates presentation. There isn't too much left to do. So we did all this. Did we do this slide? Template specializations? Good. Did we do this slide? Yes. Okay. So, continuing then, all template classes can be specialized. So here's a stack class, templatized on T, and its specialization for ints is this way. I don't know why you would, you know. Chances are you don't really need to do that. The generic one will work just fine for ints as anything else. But should there be something about the integer type that you wanted to handle differently in the stack than in the generic one, if you make the specialization, the language guarantees that the compiler will pick the specialization in preference to the generic. And you can have as many specializations as you want. If I have 7 specializations, the compiler will check when I instantiate a class or a template class or a function, the language guarantees that the compiler will check every single specialization before it uses my generic form. Okay? That to take care of the cases like Max, where, you know, Max compared the generic form, just compared pointers and gave you aardvark or zebra, whichever one was higher in memory, not lexicographically higher. And so we need, for that particular case, we need to change the definition of what the comparison means. And we did that with a string compare, lexicographic string compare. And the same thing is true of, you know, other cases. We're going to see an example or two this morning when we look at code. So here I can have a template class parameterized on more than one type, U and V. Again, remember, normally we use type name here. I've used class to make it a little more compressed for these slides, but type name is to be preferred. You'll see in my code I tend to use type name. They're equivalent, you know, but this is the old style. So here's the generic form of widget class, templatized on U and V, and now here's a partial specialization. So what I'm doing is I'm specializing the V type to be an int, and this code will be different than that code. Otherwise, why have the specialization? Okay. It may add, modify, or remove members to suit the parameter, that particular parameter. Change the code. So here's a fully generic class, UV widget, and here's how I would instantiate that, you know, fully generic class. Now here's a partial specialization. I've specialized V to be a double, so I just say now template class U, now widget of U and double, okay? And now if I instantiate it with string and double, now with this specialization, it'll pick this over this. Now, if I come along and do a complete specialization, template, nothing, widget of string and double, okay, now if I instantiate on string and double, it'll choose this in preference to this, in preference to this. Okay, it'll pick the most specific specialization. But if if these are my only specializations, so here I have two specializations. If I instantiate this on int and double, okay, then it'll choose this one, but it won't choose this one because this is string and double. So if I chose it for int, okay, I have a specialization for double, so it would use that. Okay. There's some material on containers, which I'm going to skip in preference to looking at some code. This isn't, the material here is not going to change how you write typical project code. It's concerned with the mental models you use when you design container classes, the STL, for example. But, you know, sometimes your classes are container classes, too. But in a sense, DB core is a container class. But, you know, so go read this, but it's not high priority. You know, there's some basic ideas that say, you know, when you write containers, write them this way. So if we have time later on, not today for sure, but I'll come back and cover this. But, you know, I think the material is quite straightforward. You can read it and understand it. So with that, let's go look at some examples. Okay, so in this template code examples, there's just this just implements, with a couple of additions, it implements what was on those slides. What was on the presentation slide, the code there, there's a max, there's a stack, there's a swap. All those things were in that, you know, mentioned in that presentation. This just shows you, this just writing the code behind those examples. Template techniques. Now, so let me pull that up. This is template techniques is in SU repository CPP templates. SU repository CPP, and now this is template techniques. So here you see, there's some stuff I'm not going to talk about. There's a curiously recurring template pattern that, you know, I won't talk about now. There's some places where it's used, and it has this funny name that was given to it by Jim Coplian years ago, okay? So there's an invoker. I'm going to talk about the same kinds of things in another example, so we won't talk about it now. I'm going to go to these things called issues. Now, let's set this as startup. Hello, mouse, come on. Why aren't you letting me right-click on that guy? Visual Studio, are you here? Sometimes it takes a little while. Yeah, there we go. Set a startup project. So this is a so some of these things called issues are language syntax. A couple are not. This one is a language syntax. So here I have an untemplated class, and I have a template member, template type T, T star clone, and I'm returning a copy, of itself. And why, it doesn't matter, okay? The point is just the syntax. We'll see some clone classes in a couple of minutes. So now, when I invoke it, I say x star pointer, new x dot template of clone. So the clone is returning me a pointer to an object on the heap of the x class. But now, instead of saying x dot clone of parens, two things have happened. One is I've said angle bracket x, and the reason I need to say angle bracket x is that the only place clone appears is in the template type appears is in the return type. Okay, it appears internally, but as far as the compiler sees when you invoke it, it's just the return type. And so the compiler inferencing needs a little help to figure out what it is, and so you type clone of x. Now, a lot of times the compiler the template inferencing works just fine, but every now and then it needs a little help, and it'll tell you. Normally, I don't write these, okay? Almost always when I return, when the only visible template, only place that the template parameter is visible is in the return type, almost always you need to provide this. That's just helping the compiler infer the right type to instantiate for the clone. The other one is the fact that I have template here with a space, x.template space clone. Visual Studio Compiler, if I left that off, if I just said x.clone of x, it would work just fine. But the language standard says this is the way you write it. Stroustrup says this is the way you write it, okay? And so just because Visual Studio does it just fine without the template, some other compiler might not. Clang might not. GCC might not. G++ might not. I don't know. They probably do. Visual Studio is the 800-pound gorilla, and whatever it does, most everybody else does too. But no guarantees. So you ought to do with the language. So the language says do this. So these are just little reminders, little quirky syntactic things. That's what this set of code is all about. Okay, issue 2, type name. So here we see this funny thing, type name. What the heck is going on there? Now, so this is a declaration of a function, but the compiler's looking at, the compiler really needs a little help to infer that I mean this to be a type that's returned by func. Okay. And here I need to help the compiler infer that this is a type. Okay. C::: iterator, in this case, is a type. But C::: iterator might be an instance, the name of a variable in the C class. Okay. And so, is this a type, or is this the name of a variable? It could be either one. In this context, because it's returned from a function, it isn't. Okay. But the inferencing is not quite strong enough to detect that. The inferencing happens pretty locally, and so it can't. It says, hey, I can't tell whether that's a type name or a variable name from the C class. So first of all, let's run it. And if I remember right, this does nothing. Yeah, it does nothing. I'm not printing anything out, but it's compiling. But now let's just do this. Notice it says iterator dependent name is not a type. That's the giveaway. If you see that message, if you see this message, something dependent name is not a type, it means you need a type name. If this said C:: wombat, then this would say wombat dependent name is not a type. Okay? So if you see that, that's just saying, hey, you need the type name. So so now it'll compile just fine. Now this one, it turns out this used to be needed but is no longer needed. So now if I compile it, it builds just fine. In Visual Studio 2015, you had to have that. But the type inferencing is getting a little smarter. Okay, that's what happens. Each version of the compiler, the type inferencing, and the standards too. The standards are forcing the inferencing mechanism to get smarter and smarter and smarter. So, so here's what I do. How do you know when you need to use that? And my answer is, the rules are kind of subtle and not laid out anywhere, and I don't worry about it. I never use it until the compiler natters at me and says dependent, what does it say? It says dependent name is not a type. If it says that, type name, done. It compiles, okay? So, you know, that's not, C++ is a large context-dependent language. This is context-dependent language, okay? So, and that's, you know, it would be nice if it wasn't so big and it wasn't so context-dependent. That would be preferable. I love C++. I think it's a great language. I would rather work with C++ than anything else, but it is big, and it is context-dependent. And so it takes you a while, but here, the reason I'm showing you this is that just to show you, you know, there's a couple of quirks, and again, I don't worry about it. I just write my code, and if the compiler tells me, then I go insert it. Okay, now let's look at something else. This is a different kind, this is a design issue here. So here, I have a class clone that's going to accept a prototype. So it has a method, accept prototype. This is a prototype of T. So this class clone, its job is to make a copy of the T prototype. So I'm going to give my clone function a prototype to copy. Why would I do that? So it may be that I need a whole bunch of these objects, and I want them to all have this state, and it takes some widgy little, you know, monkeying around with the instances to get them into that state. And I don't want to do that with 30 of them. So I do that complicated state setting in one, and then I copy 29 times. Okay? That's what this is for. So I have a class clone, accepts a prototype of type T, and make just returns, this is a copy construction of type T, of the prototype. This is a great question for a midterm. What is this code doing? Okay, so great. There we go. Away we go. Okay, and and by the way, the clone type is not going to delete, even though it created an instance of that prototype, it's not going to delete it because it handed it out to you. Think of this clone as a smart new. Clone doesn't know when you're done with that object. Only you do, so it's your responsibility to delete it. And, you know, if you supply this class to users, you'd want to tell them that. Okay, so now here's a type that I'm going to create. All it does is announce itself. I've been created as a copy, blah, 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 blah. So this is the type we're going to use. And here is a policy-based creator. So now I'm going to create an instance of this type, and my creational policy is this prototype, copy a prototype. But I could have another policy which is create a default object. I could have another policy is create one on the stack, don't create it on the heap. Or something. Okay. Or reference this object that's already on the stack. Okay, or something. So this is a policy. So a policy is a template argument. This is the main thing. This template, this is the main argument. It says, I want you to create one of those. This is a modifying argument, like an adjective or an adverb that says this way. So think of this as the verb and the adverb, or adjective. Adverb. Run, quickly. Okay. So, if I'm parsing my English correctly, some of you guys probably, it's been so long ago since I've been in an English class that I don't remember, but anyway, so creational policy, and my, created make, and now I just say creational policy, : make. And some other policy, would make a default object, and some other policy would return a reference to something on the stack or whatever you want, okay? So I might want to do a whole bunch of different things. Now here's main, and so I say create a type, the prototype, and now creator, created type, clone of created type, cloner. Now, I don't like this. The reason why is this needs to be cloned, this needs to be templatized on the same parameter. I know that because I designed it. But a user may not know it and may try to instantiate on different types. Not good. And also, even, if you're going to guarantee that these will both use created type, why do I have to specify created type twice? So let's see how you would change that. So, this works, and it runs, and it works fine. Let's just run it. Okay? I've been created as a copy. All right. Now, let's look at 3B. I'm going to make a subtle change here. So here's 3B. Clone class exactly like it was in the previous example. Created type exactly the way it was in the previous example. The only difference is in this policy-based creator. Now I say template class created template class created, class creational policy. In the previous 3A, there was no joining of those two types. They were just independent types that I wanted to be the same. I depended on the user making them the same. Now I'm going to force them to be the same. Created, template class created. Now I guarantee that they are the same. Safety issue resolved. On Thursday, I talked about template parameters, and everybody was saying, what is this crazy guy talking about? This is a template parameter. This is a template parameter. Here's a template parameter that itself is a template. That's why it's called the template parameter. It's a template parameter. Okay? Yes. Okay. Now it has one other nice thing about it, and that is now when I come to create an instance of the creator, I say created type clone, and I don't have to say bracket created type bracket. So it's easier for the user to use. Okay? Yeah. So you say, but it's a lot more work. This is more complicated for me to write that. So you're going to write it once. And if it's a good piece of software, it's going to be used hundreds and hundreds of times. So which is preferable? To have the designer save 10 minutes, 5 minutes not doing that, and have all 100 spend 10 minutes to try to figure out, what went wrong because I used two different types, or have the designer spend 5 extra minutes with slightly more complicated code, and now every user gets it right automatically. Certainly you want the latter. I hope you want the latter. There are developers whose attitude is, make it easy for me, the heck with all the users. And a lot of shelfware is written that way. You know what shelfware is? Highly technical term. It's software that you run once and say, ugh, this is awful, put it up on the shelf. Never use it again. That's shelfware. Template parameters, is that what that's all about? Yeah, that's what that's all about. Okay. So, partial specialization. So this is a little example of why we might want to do partial specialization. So here is a smart pointer class. Now, don't use this, don't write your own smart pointers classes. The library has a nice standard unique pointer and standard shared pointer. You're comfortable by now, I hope, with standard shared pointer because I used it in an XML document. Standard unique pointer, if I do an assignment of one standard unique pointer to another, what happens is I transfer ownership of what the source was, whatever instance it pointed to. When you do that assignment, this guy deletes his instance and now accepts the pointer to that instance, and this guy's pointer goes to null pointer. It's a transfer of ownership. That happens if I assign or if I copy construct a standard unique pointer. A standard shared pointer, what it does is, if I assign one pointer to another, it has both of them point to the same object, but it has a reference count, and it increments the reference count. So if I copy construct or assign a shared pointer, increment the reference count. And what happens is, when one of those smart pointers goes out of scope, reference count is decremented. When another one goes out of scope, reference count is decremented. And the way it's designed, here's the many instances of that shared pointer. There's one block, unshared, well, it's shared block, one block that holds the reference count. For all those smart pointer instances, they're all referencing that one shared reference count. When the reference count goes to 0, that block deletes the object. Okay. But this illustrates the idea behind specialization, one of the ideas. So here I have a smart pointer class, and the idea is that I can point to an array of t's. I specify the size, I specify t, and here, I can pass it a pointer to the array, and I create a new array of size, blah, 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 blah. I delete with brackets because I know it's an array, and I can index it. Okay, great. Now, I'm going to specialize it to the case where t is 1. I'm sorry, where the int is 1, size is 1. So now this smart pointer is only going to point to a single object on the heap. So now I just create make my pointer equal to that original guy's pointer, okay? And I'm sorry, I'm creating a new instance of what the source's pointer pointed to on the heap. But now, notice that operator bracket and operator plus aren't supported. I don't even have them in there. They're not there. They're gone. Because it doesn't make any sense to index a collection of one item. Okay? So, totally different. Contents are different, and some of the methods went away. Absolutely fine. These are two different classes. They're two different classes. I can put anything I want into either one of them. They should be semantically similar, otherwise why do it? Okay, but the condition has changed. So now instead of pointing into an array, being a smart pointer into an array, I'm a smart pointer into a single instance, and so it's changed. I can write anything I want in that code. Okay, so, and you can run it, whatever. Now, partial template specialization, let's see what I did here. Yeah. So here I have two different cases. I have test 1 of class T test 1, unspecialized, and now I specialize it for a double, and I print out that it's specialized. I specialize it, I guess that's all I did. I specialized it for a double, and I print out that it's specialized. Here's a second demo, class 2, that has 2 parameters, and I first specialize the first parameter on an int, and then I specialize both parameters on int and double. Okay? And now I demonstrate it, here's my test 1 for a char, test 1 for int, this will be specialized. No, it's double this, test 1 for double is specialized. And here's char int, int double. So when we run this, you can see I don't get, on the first test 1, I don't get the specialized until I instantiate on a double. For the char and the int, I have the generic form. The language guarantees me that if I match the specialization, it will pick that first. And I can have as many specializations as I want. If I have 7 specializations, the compiler is obligated to check all 7 before it chooses. If it doesn't get matches on any of those 7 specializations with the type that I'm instantiating on, then it uses a generic one. And here's the test 2 that had 2 specializations. So, and I'm illustrating that if I don't match, I'm unspecialized. If I match the partial case, I pick the partial one. If I match the total, I pick the total one. Okay. So, guaranteed that it will use the most specific specialization. Okay. Language guarantees that's very, very, very useful. We can't do that with C# and Java generics. C# and Java generics do not have specialization. They can't because they aren't resolved at compile time. They're really a runtime, they're resolved at runtime. So it's really casting. It's really hidden casting is what C# and Java generics are. C++ templates are a compile time artifact. It's one of the things that makes writing a C++ compiler so difficult. Okay. So. Yes?
Suppose I have a class containing two template classes, class T, class U. I have a class, have two template classes, class T and class U, and I have two specializations. The first one, string, class T, class U, and the second one is class T and int. And I pass it with a class string int, and which specialization will the compiler pick up?
So you have two partial specializations, and that's an interesting question. You shouldn't write code like that because it is ambiguous. I hope the compiler would refuse to compile it saying it's ambiguous. I hope, but I'm not sure. Okay. I never tried that case. Good for you for thinking of it. I never tried that case. But you would like the compiler to fail the build because it's ambiguous. The compiler is pretty good about failing ambiguous cases, so I suspect that that's what it'll do. It's a good question, by the way. Pat yourself on the back. What's your name?
Sexy.
Okay. Pat yourself on the back. Okay. Template parameters we already talked about, and this one is a little more complicated. I keep meaning to remove it because I already talked about template parameters in the issue 4 or whatever it was. So, but I do want to talk about test types because this is our first glimpse at template metaprogramming. Our what? So here, is_char, template type name T, struct is_char enum value equals false. So now enum is a named constant. And it has this value false. And so value is a name known to the compiler. And when it compiles this, it'll have this, it'll be typed as false. Now I have a specialization on char, struct is_char enum value equals true. So what happens is if I say is_char of double, it should value should be false. If I say is_char of A, it should be true. Okay. So and this is resolved at compile time. This decision was made at compile time via the template specialization. It turns out that in order to implement templates the way they are currently specified, the compiler, C++ compilers have to provide a language that runs at compile time. It's a functional language. For those of you who are computer scientists and have taken Haskell or are taking Haskell or will someday take Haskell, okay, it's a language somewhat like Haskell. You know, in many ways not like Haskell at all, but the same ideas. Its data is all constant. You can't have variables at compile time. You can only have constants. And if you want to change that constant, you gotta create a new one. And at the end of the course, if there's time, I'll walk you through that a little bit. It's called template metaprogramming, and it's mind-bending. I have some examples, and every now and then I'll get up in front of class. It varies from year to year, but I'll get to that and say, gee, what did I do here? That's weird. But now, is array. So let's look at is array. Here's another example. Is array. So now, all of these, by default, all of these type tests are false. They're only true for that one case where it is. So A of n, that's an array. So that's true. All the other cases are false. And so on. You know, is pointer, blah, 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 blah. Now, what you have to understand is that those values are set at compile time, but you can't see them except until you get to runtime. So here is, in main, if is char of int colon colon value, that'll be false because int is not a char. So what it'll do is int is not a char. Okay, but now type def char char type, if is char char type value, this will print true. Char type is a char. Okay, so I can only see them at runtime, but the evaluations are all done at compile time. So let's just run it. Int is not a char, char type is a char, x3 is an array, x star is not an array, x is not a pointer, x star is a pointer, const x star is a pointer, const x star is a pointer, volatile x star is a pointer, x star is not a pointer to member, y of x colon colon star is a pointer to member, and this is a declaration, you know, member pointer declaration, you know. So that all works. It works. And you say, that's a stupid code trick. Why would I ever want to do that? Sometimes in a, when I'm writing template functions, they haven't been instantiated yet, so I don't know what the types are, but I need that information. I can use this. There is a doctoral student, candidate in our department, Scott Constable, who took this course either last year or the year before, I've forgotten which, and he is using template metaprogramming on his thesis to write compilably secure code. Code that is secure by compilation, by checks that are made at compilation, using template metaprogramming. You know, if we have a little time, which we almost certainly won't, but if we have a little time at the end of the semester, I'll ask him to come in, and if he'll come in and talk with us a little bit about it. So, but he said, you know, when you went through that, you know, when I was in class, I said, oh, that's kind of interesting, but it's just a code trick. You know, I'm never, who's ever going to use that? And I said, guess what? It's a core part of my dissertation. So, what you're doing, one of the things you do with this template metaprogramming is you are exchanging runtime cost for compile time cost. You're running a program at compile time, and then you run it 1,000 times once it's been compiled. You don't pay that cost to do that computation because it happened once at compile time. You know, every time you change something, you rebuild it, it's going to take longer. But also, when you're writing template functions, there's things you just can't do without a little bit of metaprogramming. Okay, so. All right. All right, so that's that. Now, there is fully functional C++ properties courtesy of templates, and I like the syntax. So I wrote this, I created properties for C++. Doesn't have it, but the template language is powerful enough that you can do that, and I did. And I like the syntax real well. There's only one issue. I don't use them. There's one reason I don't use them. In order to get the value out of the property, you got to use a cast. And it turns out that cast always makes a copy, even if you're casting to a reference type. It shouldn't, I would think, but the Visual Studio compiler was doing that, and I went and looked at the standard, and guess what? The standard says that's what we'll do. Even if it's a reference type, we make a copy. And there's a safety issue associated with that. But the problem with that is now, if I make so for remember the testing I did, I was doing this well, I could have made a database property, and I wouldn't have public data anymore, but it would be just as accessible, easily accessible now, because it's a property. But now, every time I got the database, I would make a copy of that whole database. Okay? So I don't use those properties, and I wouldn't suggest. There may be a way to do it without casting, but I can't figure out, I haven't figured out yet a way to get a nice property syntax without casting. So I don't use it. But anyway, you can take a look at it and you can see, let me just do a quick click and show you what I mean, functional properties. So let's go here into CPP properties. No, I want CPP properties.cpp. Where are you? CPP. So here's its use. So here I can say, class X, property standard string name, property double is mutable, property const double pi, and these work just like C# properties. And they're encapsulated. They're really getters and setter methods working under the covers, and if I need to check, do a validation or an authorization or check on, is what you're doing not allowed on that particular value, I can do those in the getter and setter. So from a from a syntactic point of view and a semantic, in a behavioral point of view, it's great, works just fine, except that one performance issue. Every time I get out that value, I am doing a copy. For doubles and ints, it doesn't matter. They're just fine as doubles and ints. But for a database, if I make a database property, I'm going to make a copy of the whole darn database. So not a good idea. So I don't use these. But the point is that templates now allow me let's look at CP properties.h. So now, I have class property. So remember, I said property, angle bracket up, blah, 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 blah. So class property, and here I am constructing it to load in the value, and here is the const. Here is the cast. So this is how I get a value out of that property, by casting it out. The problem is that even if T is a reference type, it still makes a copy. You wouldn't think it would. Why do you? If I have T by reference, you'd think it would return a reference, but it doesn't. It makes a copy. I think what it does is it makes a copy and gives you a reference to the copy. Okay, thank you, thank you. But the standard says that's what it's supposed to do. So anyway, all right, so simple demo of callable objects. So this is in callable object simple demo. So let's go there. So here I am, repository CPP, simple demo. Now, let's quickly go through it, and then I will motivate it. I'll tell you why we're interested in doing that. So bear with me. So here's callable objects.cpp, okay? And so here I have a function that accepts, it's a template function that accepts, this is just a type name, this is just like T. I called it callable object because I intend to pass it callable objects. I intend to instantiate it with callable objects, and I'll tell you what they are in a minute. So this will execute any callable object that has a signature, I take no arguments and I return nothing. And so this is just executing that callable object. A callable object can be a function or function pointer, a functor, and if you don't know what that is, I'm going to show you right now, or a lambda. And if you don't know what that is, I'm going to show you now. And then after we see it and see how it works, then I'll talk a little bit about why this is important. So here's a callable object, this function hello. And by the way, hello is just a function pointer. The compiler has a variable whose name is hello that holds a pointer to that place in the code. Now here's a functor. A functor is any class that implements operator paren. And the reason is that I can call on an instance of that object, I can say paren like it was a function, and it invokes this operator paren. So here, so now what's happened is I pass in a message in the constructor, and now operator paren just prints out that message that I sent in earlier. But notice that this is a block of processing and data together that I can pass around. I can put it in a queue, I can 2 days execute it 2 days later, whatever. Store it in a database. Okay. So here's another callable object. This is a lambda. So the lambda starts right here and goes to here. That's the lambda. Anything that starts with bracket with nothing glued immediately before that, okay? So either a new line or a white space, some kind of white space there. The compiler says, aha, lambda. And for, don't worry too much about this equal sign. I'll if we have time today, I'll talk more about that. If we don't, I'll talk about it on Thursday. But this is lambda. This is the arguments that I pass it. In this case, nothing, but I could specify some arguments here. This is a processing body. And notice it uses message from here. Message was declared outside the lambda, but in the scope of the lambda. What happens is the compiler is creating a functor from this code whose operator paren implements this block of code, and that has a data member message with that value. The compiler wrote a functor. So if I can take that functor instance and pass it around, then the data and that function, that block of code, are going to go wherever it's just like any other class, okay? But it's a class that I can call like a function because it has operator paren. Now a lambda, is thought of as being an anonymous function, anonymous block of processing, whose type is unknown. You can run type ID on it and find its type name, and it's some weird, totally nonsensical thing that the compiler just generated as a random thing. Okay, so so these turn out to be very useful, and I'll explain why in a couple of minutes. Now, sometimes I need to have something to hold on to those lambdas with, And so I can say standard function with the signature of this lambda, so no arguments, and it doesn't return anything. There's no return here anywhere. So void, no arguments. That's the standard function, and I can bind it to this lambda. Standard function is a construct that was provided as of C++11 that will bind to a lambda, to a functor, or to a function pointer to a global function. It'll bind to any of those three things. It's designed, a little bit of template magic going on inside, so it can bind to any of those three different types. Now, remember that the executor is just a simple thing, template function, taking a callable object, and it executes it. That's all it does. So here is my executor executing that function pointer, hello, the function. It's now I create my functor of mf, hi, and now I'm executing that functor. It's just calling mf print. And now executor of sfun is calling sfun print. So that executor can execute any of those types. And by the way, I can define a lambda inside the executor without that standard function. I just write the lambda right in the calling argument of executor, and that works too. Why is that useful? You say, oh, this is another code trick. Come on, Dr. Paul. Yeah, all these code tricks. Stupid code tricks. Suppose I was building a thread pool. You're going to use one of my thread pools in project 3 or 4. Thread pool I wrote. So a thread pool is something that starts up a bunch of threads and passes it things to run in a queue. You put work items into the queue, and the thread pulls the work items out of the queue and executes them. And you say, but a thread has a function. You can't change it. And it only does that one thing. That's all the thread can do, and that's true. It can only do that one thing defined by its thread function. When that function ends, the thread dies. That's the way threads work. But suppose in that queue we put a callable object. And what the thread function does is it keeps going back to the queue and pulling out a work item, and it executes it. Goes back to the queue, pulls out an item, executes it. Goes back to the queue, pulls out. So this one function, that function is given a queue and says, keep pulling work items out until you get some signature thing in there that tells you to quit. So now I can define work items as a function pointer. I can define them as a functor. I can define them as a lambda. Anything I want. Having that flexibility is really, really useful. Helps me write simpler code. That's why this is important. It's not just a silly code trick. Let's run it just so that you're totally convinced. I hope there's some skeptics in there and say, yeah, that's not going to work. So let's run it. Hello from hello, hello from functor, hello from lambda, hello from another lambda. Okay, all there, it's working, baby. Okay, so okay, so now there's some functor examples here. Yeah, I'm not going to talk about these functor examples. You can look at them. Recommend you do. I want to take a look at this. How are we doing time-wise?
We're having about 14 minutes and 41.
We have until 50. Yeah, okay. So this is demonstrate. So this is callable object demo. So let's come up here to CPP and do callable objects demo. Not the simple demo, but the demo. Now, what I wanted to do is show you, so I tend to call my functions that execute callable objects as invoke. You call them whatever you want, but executor or invoke. So I have a function that will accept a callable object of type T that takes no arguments and returns nothing. I have a callable object, a function that runs callable objects that accept a parameter and return nothing. So now, template type T, the type of callable object, and type name A, the type of argument I'm going to supply that callable object. And so T of T, A of A, T of A. Now, the last case is I want a callable object T that accepts argument A and returns something of type R. Totally wide open. R could be a bool, R could be an int, R could be a double, R could be a widget. Okay. So what I'm doing is I'm just taking that basic core idea we looked at in the previous demo. I'm just expanding its generality to see how we do it. Okay. So now I have three things we're going to look at and invoke for. There are functors, there are lambdas, and there are function pointers. And surprisingly, function pointers are the most complicated. So let's first look at the functor. So here, class functor, type parameter. So I have this functor accepts a parameter P, stores it away, and then when you pass it to its operator paren, another value for that parameter, it compares the two and tells you whether they're equal or not. Okay? So let's go look at functor CPP. So here, I am creating an instance of the functor, functor int f42. So I'm giving it the value 42, and now I'm passing it into its operator paren, the value 42. These are different things. Here I'm constructing an instance of the functor and giving it the value 42 to store away in its parameter. And here I'm passing its operator paren. This thing is absolutely equivalent to saying f dot operator paren of 42. Same thing. That's why we call them functors, because they look like a function call when we invoke them. So so I did that for an int and for a string, and I'm just invoking them, you know. So first I call them, and then I invoke them with a callable object. So let's just set that up as startup and run it quickly. So I first passed it 42. Functor's parameter and value are the same. Now I passed it 43, and it says functor's parameter and value are different. Same thing with strings. Okay. 42, you know what 42 is? It's the meaning of life.
That's the lucky number for the
Hmm?
That's like the lucky. Oh, that's 44.
42 is the meaning of life. How many of you have read The Hitchhiker's Guide to the Galaxy? Raise your hand if you've read The Hitchhiker's Guide to the Galaxy. Good. Yeah, good. Good for you guys. You too. So all the rest of you are culturally deprived. This summer, go read The Hitchhiker's Guide to the Galaxy. Wait till the summer, but this summer, go read it. So the story goes, I've forgotten the guy's name, but he's an Earthman, Englishman, you know, and it turns out this alien culture is putting through a galaxy bypass, and they need to destroy the Earth to make room for the galaxy bypass. And so they do. They blow up the Earth. But this one guy, gets sucked up into the alien ship before Earth is destroyed. Then it's destroyed. It's gone. Okay. But he spends this journey, Hitchhiker's Guide to the Galaxy. He's taking this journey through the galaxy, visiting a whole bunch of different civilizations. And in one place, he comes to an advanced civilization that has a very advanced AI. This guru AI that runs the whole civilization. And this Earthman gets a chance to ask it any question. He says, so the Earthman says, what is the meaning of life? And this advanced AI chugs away, and 5 minutes later it comes back and says, 42. Okay. That's funny. I think it's funny. Maybe you got to be a little. Anyway, it was written by Douglas Adams, who's really no longer with us, unfortunately. A really cool guy. So, but you'll see me use 42 every now and then. So that's where it comes from. But anyway, so that's functors. Here's lambdas. And I'm going to use the invoke again. So here, you know, I have a lambda, and now this lambda, here I'm using auto instead of standard func. Either way works. And this is returning. So now I'm going to invoke the callable object that returns. So I have some invokes that are template overloads of invoke, okay? And it's going to call the one for the return that has the return type. So I pass it a string, and I'm returning a string. And what this guy is doing, what this lambda is doing is here it says return message plus epilogue, but up here I define the string epilogue. That's all, folks. So this is defined in the scope of this lambda, and so the lambda is capturing epilogue. Remember that this is the compiler just creates a functor whose operator paren is this block of code, and that has a data member of anything that's used. So it has a data member for epilogue. I'm going to pass it the message, okay, as an argument to operator paren, but epilogue has to be a data member stored away. So the compiler just creates that. So this is a shorthand way of creating that functor. Okay. So what we're seeing here, if we run it, okay, so that's the lambda doing its thing, returning its value, using its captured value. So, and I did it, so two things happen here. So one is, here, I'm just invoking the lambda itself. I'm calling the operator paren on the lambda, okay? This is auto lam, and so this, I could have said lam.operator paren, and returning the string that's returned. I'm printing it out. Here, I'm using the invoke. So I'm using that overloaded invoke, Now, I got to tell it that the return type is standard string because remember the type inferencing for the arguments that are return values, the type inferencing isn't smart enough to pick that up. So I got to tell it that this is the invoke for this return type, and it's taking this argument, so it's just using that overload. Okay? So now, if I have those three invoke functions, I can pass it anything that's callable and is void void, void some argument type, or return type argument type. All works. Flexible. This is all about writing flexible code. I write that invoke thing once and I never write it again. I just keep passing stuff to it. So for something like a thread pool, really useful. Now, we don't have a lot of time left. I want to just quickly point you at this function pointer. Because function pointers are quite straightforward until you start getting into pointers to member functions. A function pointer is a callable object. A function pointer to a global function, to an unbound function, is a callable object. A pointer to a member function, to a method of a class, is not a callable object because now I got two things. I got the pointer and I got the instance. So I have to use that instance to call that pointer. I can't just call the pointer without the instance. So it's not a callable object. And there's a couple of ways to handle that. The syntax gets tough as you get into using that so here I am demonstrating member function. The syntax gets, you know, what on earth? My head is swimming. That syntax is real. So I did this for two reasons. Because every time I write that kind of syntax, I stumble around with it, don't remember it, you know. So now I got one place where I'll remember it, and now you have one place where if you ever need it, here it is. I wouldn't lose a lot of sleep. I would take a quick look at it and get roughly the idea of what's going on. I wouldn't lose a lot of sleep about figuring out exactly when you do this or that, okay? Because you don't use pointers to member functions very often. When you do, you got this is your reference. Okay, we got to pack up and get out of here. The next class is foaming at the bit to get in. So there will be open office hour today at 2 o'clock, and there will be a help session on Friday. So we'll see you all either this afternoon or Thursday, whichever comes first. You can ask questions after all. Just let me back up and get out of here because let the other class in, and then we can talk. I'll sign it out in the hall. Okay.
尽量来，然后写。
哦，我知道，因为那个。
我现在有3个。
我也写是一家站点。谢谢。你是不是有个 XML 连接格子？那个时候没有。